Lecture 10, Concurrency and Parallelism. Now, concurrency and parallelism are topics hopefully introduced to you previously in a different course, preferably one that was specifically about concurrency, or at least something that touched on it in a non-trivial way, in which case, well, you have a reasonable understanding of what the subject is about and how it works. Nevertheless, we'll try to give you sort of a quick recap, just to be sure that there's no possibility of confusion. And we'll start off by talking about limits of parallelization. So think about when you're writing your code, what limits it? Well, one thing that potentially limits your code is the worst case scenario for the runtime performance of your algorithm. An algorithm that's order n cubed is so much worse as it gets bigger than one that's order n. It's just kind of not sensible, and you have to make sure that you're using the correct algorithm approach for the problem that you're facing. Doing insertion sort on a small array is fine and is in fact recommended, but doing it on a huge array is madness. And choosing a good algorithm is very important if we want things to scale, but you know that already. You're not in a fourth-year course in engineering for me to tell you that you should use quicksort instead of bubble sort, right? Like that has been established previously. But when we're thinking about speeding up our program, and this was mentioned sort of in the roadmap, we're going to look at concurrency and parallelism to get that done. Why? Well, for one thing, it takes advantage of the hardware that we have, and for another thing, it is going to be a very efficient way of getting things done. When there are no dependencies between tasks, say, we could do them in parallel, and we could accomplish more work in the same amount of time, or the same work in less time, all of that. Now, if you remember, there is a distinction between concurrency and parallelism. Concurrency is just having multiple things in progress at once. So for a student-relevant example, if you are working on an assignment, you're doing assignment 1 of course 1, and you do the first 2 questions of it, and then you put that aside for now, and you go do assignment 1 from course 2, you have both of those in progress at the same time. You are working on those concurrently. They are not being worked on at the exact same instant. At any given moment, you are working on one or the other, but only one at a time, and that makes it concurrent. Parallelism would be if at the exact same moment that you are working on assignment 1 for course 1, your friend is also working on assignment 1 of course 1 over where they live, and that is parallelism. You are both working on different tasks. Well, there's 2 different tasks, that's fine, but if we stop time or look at it at the exact instant that is of interest, we can see there are 2 things making progress at the exact same time. So that's a key distinction between parallelism and concurrency that we should remember. Okay, and of course, if we look at our big O complexity graph, obviously, don't choose the wrong algorithm, otherwise everyone is sad. Okay, so quick reminder is that parallelism is intended as a goal to try to get tasks to run as fast as possible. What can we accomplish? How do we do it? How do we do the most work in the least time? And the main concern about that is dependencies. So what prevents things from proceeding? If you need this result before you can go on to the next step, that is a dependency, and that is going to hold us up a little bit, and something that we are interested in because it could potentially prevent any kind of parallelism at all, or at least limit it. Whereas when there's concurrency, it just means that the ordering of 2 tasks is not predetermined. If you have 2 assignments and they're both due on the same day, you could work on them in any order, really. And there isn't a specific rule that causes you to have to work on them in any particular order. If you have in a course lab 1 and then lab 2 builds on what you wrote in Lab 1. Obviously, you want to complete Lab 1 before you go on to Lab 2. That would be a synchronization point. It is a form of coordination that says this happens before that, or these things don't happen at the same time. If the concurrency parallelism stuff is still kind of confusing to you, then going back to a previous course, looking over, for example, the ECE 252 notes, might give you a decent explanation about concurrency if you need that sort of catch-up. And if you want the quick version of that, there is a synchronization PDF in the course repository, which is not extensive, but should give you everything that you need to know to get caught up on this subject. All right, so since our main focus for right now is parallelization, this is our first strategy that we will use to try to speed up our program, then our main focus is, well, how much can we do that? Most programs are defined as having a parallel part and a sequential part. And we are going to follow a rule, Emdels Law, a classic model of parallel execution, because in 1967, Jean Amdahl argued that improvements in processor design would be beneficial. In fact, at that time, more beneficial than designing multiprocessor systems. We know now that's no longer the case, but things have changed a lot in many areas since 1967, and looking over the period of time leading up to about the year 2000, it's easy to see why that was the right decision in that era. So anyway, we can use, however, this calculation to make a determination of what are the limits to parallelization. And if we say that every program has a sequential part and a parallel part, it allows us to do the math on this. And we're interested just broadly in what fraction of the program can be done in parallel. That might be very little, or it might be a lot, depending on the nature of your problem. And so if we say that S here is the fraction of serial runtime in serial execution, and P is the fraction of parallel runtime in serial execution, so the initial state, base case, we haven't parallelized anything, but just for the sake of comparison, S plus P equals 1 because they are fractions. It's the percentage of the program. And so if our program looks like this with a sequential part and a parallel part, obviously the sequential part doesn't always happen first and the parallel part later, but if you just group them up by their blocks, they will obviously be interspersed a bit. Then, well, we end up with this if we are splitting up the parallel part over 4 processors. We can take the parallel part, divide it into 4. We can do those 4 parts at the same time, or at least something resembling the same time. And we end up with a shorter total runtime, even though the amount of work that we have done is the same. So the formula that we will see here is if T sub S is the time for the program to run serially, N is the number of processors, CPUs available, but it could also be computers if you have a distributed system. And T sub P is time for the program to run in parallel. Then under perfect conditions, then T sub P is T sub S times S plus P over N. That's a simple formulation, but not the form in which we usually apply Emdels Law, because we're usually interested in calculating how much is the speed up. And so speed up is Ts over Tp, which is crushed down in the end to 1 over S plus P over N. This assumes, just using the simple formulation, there's no overhead for parallelizing, or your costs are near 0. When we talk about overhead for parallelizing, this is along the lines of handing out the work, deciding how to divide it up, that sort of thing. If the cost is near to 0, then we don't worry about it. If the task being computed takes 12 hours to compute, and you have to spend 1 extra second deciding how many CPUs we have and how to hand out the work and how to collect the results at the end, huge win. We would say, listen, as compared to the 12 hours, the 1 second is totally irrelevant, and we're not going to think about it, so we can just use this formula as it is. But keep in mind that overhead is never exactly zero, and that does occasionally mean that if you have the kind of problem where it's very simple, it's very quick, there is actually sometimes no benefit to doing a parallelization, doing a split up of the work, because the overhead of dividing it up is exceeding the benefit that you would get from it. But that is hopefully rare. In any case, like, how well does our model work? Well, I mean, here's the kind of speed up that you could possibly get based on the number of processors you have available. And you can see that in the ideal case here, this top straight line, if it's 100% parallel, then having more processors is always better. But we do eventually get diminishing returns as things go along. And if we have a 50% parallelizable problem, we're capped out pretty quickly, and our speed up never gets to be that good, no matter how many CPUs we throw at it. I mean, going back to our formula, we could argue it sort of makes sense. In a world where the program is completely parallel and we have infinite processors, then we could speed it up, infinitely, really. Okay. And a program that is completely sequential, there's nothing in it that can be parallelized, then it doesn't matter how many CPUs we have, the speed up will always be 1, because S is 1 and P is 0. In this formula, and ultimately there's no improvement that can be made. And so, yeah, that is more or less how it works. So the maximum speed up can be calculated based on this, and the asymptotes in the previous graph, as you may have imagined, are bounded by that maximum speed up. And if we just replace S with 1 minus P, so there's one less variable in this equation, the maximum speed up is 1 over 1 minus P, or if you prefer 1 over S, because as the number of CPUs approaches infinity, P over N approaches 0. And so if our parallel part is going to be 99% and we have 18 CPUs available, then we can get a speed up of about 15 times. If our parallel fraction is 50% and we have 18 CPUs, best case scenario, we get a doubling of the completion of our program, so it takes half the time, or a speed up of 2. So if you wanted a less sort of hypothetical example, if you have a task that can be executed in 5 seconds and contains a parallelizable loop, we'll say that of this, the initialization and recombination code takes 400 milliseconds. So with one processor executing, it takes 4.6 seconds to execute the loop. And if we split it up and execute on 2 processors, divide it in half, we get 2.3 seconds to execute the loop, and add to that our setup and cleanup time, for a total of 2.7 seconds. And using 2 CPUs instead of 1 means that we get a speed up of about 46%. And the thing that we notice as we move down our chart here is that with one processor we get 5 seconds runtime, 2.7, 4 is 1.55, but very quickly when we're looking at 64 processors as compared to 128, there's not a lot of difference in there. And there aren't too many 128 core laptops lying around that I know of, at least at the time of recording. It's no longer so strange to talk about 16 core laptops as it used to be, because they do exist, and they used to be a hypothetical. Like, what do you mean it's dual core? Who would ever need more than 2? This wasn't that far in the past, and so one can reasonably predict that there will come a day when there will be 128 core laptops, and some of you will have them, and you might even far in the future be watching this video just for historical kicks. On some 1024 core CPU and laughing about how in the dark ages, can you imagine that we only had 8 cores in our laptops? I mean, how did we even get anything done? The pace of technology is kind of entertaining, and one day this video will be a historical oddity if it's survived that long. Okay. Observations. Number 1, diminishing returns as we add more processors. And number 2, we converge on the asymptote of 0.4 seconds. And so we can get a speed up out of this of approximately 12.5, but that requires infinite processors and about infinite money. I don't have that kind of money, but if I did, I'm not sure I'd spend it on infinite CPUs. There are a couple of assumptions that we've hit upon already, and one of them is that the problem size is fixed. We'll break that assumption soon. Number 2 is that the programmer algorithm behaves the same on 1 processors versus n processors. That's not necessarily the case. When we are dividing up a project amongst several people, there will inevitably be additional overhead and coordination that is necessary for everybody to get their work done. And absent that, it wouldn't work the way it's supposed to work, so there will be some overheads that are going to appear. And 3, of course, we can accurately measure runtimes, so overheads are unimportant. And again, in pre-pandemic times when people commonly flew places, you have most likely had an encounter with somebody like this who has a ridiculously oversized bag and refuses to accept reality that no amount of shoving or cramming will somehow make it fit in the overhead bin. It's just not happening, and they won't accept that. And sometimes a person like this even delays the flight because their refusal to secure it correctly ends up when they have to gate check it, and it causes a big headache. And so there's a reason why overhead bin size is measured, and why they have those measuring devices at the gate, and it's because there's not necessarily going to be enough space for your ridiculous carry-on bag. But anyway, so you can, of course, think about Emdels Law at a smaller scale. The original formulation talks about just there's one giant chunk of a program and it has one parallel part and one serial part, but we know that's not true. And of course, you can imagine that a more realistic view of this is to consider different chunks of your program as being their own individual entities, and those chunks have parallel parts and sequential parts. And so your speed up is based on how well you do at speeding up different chunks, right? If we're making a change in one part of the program, you could see what the impact of that is on the overall runtime. So consider a program with 4 parts in the following scenario. Part 1 takes 55% of the runtime, Part 2 25%, Part 3 15%, Part 4 5%. In option 1, we don't touch Part 1 at all, and we have a speed up of 5 on Part 2, a speed up of 3 on Part 3, a speed up of 10 on Part 4. And in option 2, parts 2, 3, and 4 don't change, but part 1 gets a speed up of 2. We can implement option 1 or option 2, and my question to you is, which option is better? If you want a hint, well, I mean, the real hint is do the math, but if you were asked to estimate it and you wanted a hint, one thing that I remember from taking ECE 327 with Professor Agard is he would always say, make the common case fast. All right, now if we plug and chug the numbers, just dividing the program up, option 1 gets a speed up of 1.53, and option 2 gets a speed up of 1.38. So, did I give you a hint that was deliberately misleading? I don't know about deliberately, but it might have been a little bit misleading. The thing is that these kinds of problems sometimes run counter to what our intuition would say, and it is therefore important to actually do a meaningful analysis and not just say, oh yeah, I'm definitely sure that doing this will have the most impact, because our hot takes are sometimes wrong. So it's important to ensure that your position is supported by some evidence. Okay. So one of the other things that you could do, if you wished, in terms of evaluating what is the parallel fraction of a program, because usually it's not that easy to tell, is you have your original version of your program and you have your parallelized version, and you basically just do the math on what happened in actual run times. So you run the sequential version, you time it, you run the parallel version, you time it, and you compare those to give you a guess of what the fraction of parallelizable code is. And so if you are running it on your laptop and you have a 4-core laptop, you can predict with some accuracy what the speed up might be if it were to run on a production server that has 32 cores. Potentially. I mean, it won't be the only factor, but it does give you an estimate of the speed up based on more than, well, I guess the parallel part of the program is about, because that's kind of unscientific. Okay. So, yeah, the takeaway from Emdels Law is that it's important to focus on the part of the program where it has the most impact, keeping in mind that that might not be what you assume necessarily is the part of the program with the most impact. Now, Amdahl's law estimates performance gains from parallelization with some assumptions, with some caveats in it, but it only applies to solving a fixed problem size in the shortest possible period of time. And so the alternative to this, a more optimistic point of view on the subject, is Gustavssons Law. And it says that, well, sometimes what computers are good at is dealing with bigger and bigger problems. We might not be able to solve any particular problem faster, but we might be able to solve more of them in the time that we have. So you might be able to vary your problem size here in this formula n, and this might be changing the size of the input, the resolution of the grid that you are computing, the number of time steps in a simulation, anything like that. And if you're running the software that does some fancy calculation, you might need to hold the running time constant, but not necessarily the problem size. So you're willing to wait 10 hours for your task to finish. You can set it up to start. It runs overnight and produces a result, but you're not willing to wait 500 hours to get a result. So one thing that you could think about for Gustafssons Law is how big of a problem can you run in the 10 hours that you have available. And so in this case, parallelization might improve our bandwidth, but not really our latency. And in this case, with Gustafssons Law, speed up S of n plus n times p of n. Assuming, of course, the fraction of runtime of the serial part decreases as n increases, our speed up does approach n. And this works only when you have some sort of problem size knob that you can crank up. Like I said, the number of time steps in your simulation, for example. Not always that easy, not always that straightforward, but those kinds of large problems can be efficiently parallelized. Google is a good example. They do a lot of parallelization of what are ultimately very large problems. Things like, search the web for, this potato recipe. That's a big ask, all considered, because there's a huge number of websites out there, and sorting them and ranking them in some sort of relevance is not super easy as a task, because there's a lot of data to work with, but they found a way to parallelize it and make it work. So to close out the discussion and highlight the difference between Emdels Law and Gustafssons Law is if you're traveling between two cities that are 90 kilometers apart, let's say that you are in Kitchener and you are traveling to Toronto, if you travel for an hour at a constant speed of less than 90 kilometers an hour, you can never get your average equal to 90 kilometers an hour, even if you speed up quite a lot after the hour has elapsed. Right? The total distance is 90 kilometers, and if you only managed 50 kilometers in the first hour, it doesn't matter if you drive 200 kilometers an hour, your average can't catch up to be 90 kilometers an hour. However, Gustafssons Law says if you've been traveling at a constant speed less than 90 kilometers per hour, given enough distance, you can eventually bring your average up to 90 kilometers an hour. So this is, you are driving to Montreal, that's where your next co-op is, and it's a fairly lengthy trip, maybe 600 kilometers or so from Kitchener. Well, if the first hour was slow because you were driving through Toronto and you only managed 50 kilometers in the first hour because traffic was bad in Mississauga, that kind of thing, eventually, given enough distance, you can probably get the average up to 90 kilometers per hour. It might require more than 600 kilometers in this case, so might be a bit of a long trip, but also don't drive over the speed limit in a reckless fashion. That is unsafe, and I cannot recommend it. But this highlights the difference between Emdels Law and Gustafssons Law in a driving-related analogy.